Sarah, so it's physics time. Sarah, so it's physics time. Sarah, so it's physics time. Science rules. Sarah, so it's physics time. Inertia is a property of matter. Sarah, so it's physics time. T minus 7 seconds. Sarah, so it's physics time.
Well, hello there! Welcome to today's episode of Sarah, so it's physics time.
Today we will be talking about physics.
Specifically, electromagnetism.
More specifically, induction.
Even more specifically, inductive loop traffic detectors.
Now you might ask, Sarah, so what is an inductive loop traffic detector?
Well, sit back, relax, and let's find out.
Let's set the scene for you. Traffic lights. They're everywhere.
Everywhere. At most lights, when a car pulls up and there is no other traffic on the road, the light changes and allows the car to proceed almost immediately. This is all thanks to vehicle detection induction loops underneath us.
Inductive loops are the most common type of technology used to detect vehicles. Essentially, a coil of wire is embedded in the road surface. In order for them to be installed, a groove is cut in the asphalt the wire is placed. Then the area is sealed with a rubbery compound. You might have noticed this on a road before and not even realized what it was.
The most important thing to remember about triggering these loops is that you need a substantial amount of metal.
We decided to go back to our lab and make a model to demonstrate this process for you.
Back to the lab! Welcome to the lab. So here we have a mini car, and here we have a road. Now we're just using plain old black paper, and this works because the material of the road doesn't matter as long as it doesn't affect the inductance of the loop. Underneath the road, you can see that we have an inductor. Now a normal inductance loop traffic detector would be much larger, around the diameter of a typical car. Now if we follow the wire, we see that they end up in a breadboard. Not actually, this is really a breadboard. A breadboard is a super complicated, crazy, scientific box thing with wires, and it will help us in this situation because we can use it as a way to program our stoplight without the high-tech and expensive program that they use in real stoplights. We connect the breadboard to an energy source, which is a battery in this case, and the breadboard program would then connect back to the stoplight. The stoplight has your typical green, amber, and red lights on it. Now we will model a situation in which an everyday businessman tries to get to work. Without an inductor loop, we can see that our businessman would be stuck in traffic at this light for quite a while. But with the inductor, the traffic light becomes smarter and it becomes a friend to our businessman. The inductor senses the metal in the car and tells the program that there's a car waiting. Then our breadboard comes and does its thing and eventually tells the stoplight that Mr. Businessman's light needs to turn green. And there you have it, a more efficient traffic light.
Now that we've seen inductors work, let's discuss how they work. In the case of roadway inductors, wires wrapped in a rectangular coil called a solenoid, which has a number of turns. A device is added to the wire to measure the inductance of the wire. The inductance within the solenoid with an absence of metal source is used as a control. And when a car, and thereby a large electromagnetic source, drives over the inductor, the metal from the car induces a current in the loop. The detection of the changed inductance sends a signal to the traffic controller that indicates that a car is waiting, and the traffic lights will change according to the program. Now, let's attempt to go a little more in depth on the programming of this inductor. Now, we can't afford the intricate and expensive traffic controllers that the state uses in the real roadways, but we attempted to create our own program that would detect a metal car just the same. Unfortunately, we weren't completely successful with our program due to our lack of knowledge of electrical programming, connectivity, coding, wire placing. But what's important is we tried, and we'll try and explain the elements we couldn't get to work. Here, you see the base we worked with, called a breadboard. This is used to connect all of our wires. We used a 9-volt battery as our energy source and connected it to the breadboard. Here, you can see a simplified drawing of the circuit we replicated. It has a resistor and a light bulb in series, and those in parallel with an inductor. We used an ammeter to measure the current going through the wires. In the absence of a metal source, the inductor will act like a wire in this circuit, and almost all the electrons will travel through the inductor path instead of the resistor and light bulb path, since the inductor's path has a nearly negligible frequency. But by putting the metal car over the inductor, the metal should alter the magnetic field within the inductor, and therefore change the inductance, which will decrease the amount of current going through the inductor path. Unfortunately, we could not get this concept to work. Next, the increase in current going through the resistor and light bulb will ideally have a sensor built in that would recognize the increased current and connect to a program in the stoplight that would cause the light to change to green so the waiting car could pass through. Unfortunately, we are only Sarah and Soph, and we do not have the ability to configure such a program.
So if you're ever out for a stroll and you want the traffic light to change to green, don't push that crosswalk button because we all know they don't work. Instead, have your handy dandy neodymium magnet ready. Tape it to the bottom of your shoe. And stand in the middle of the road until the light changes to green. Now that you know all about traffic light induction loops, you can be a master of the road.
Thanks for tuning in. We hope you enjoyed this episode of
Sarah, Soph, it's physics time. Bye!